Hey, welcome. Today we are going to take a journey down a path we all think we know, the number line. But we're going to build it from scratch, and I think you'll be surprised to find out that this simple line is hiding some absolutely incredible secrets.
So, to get our brains warmed up, let me ask you this. How many numbers are there between 1 and 2? Just think about that for a second. Your gut might say, I don't know, a few? Maybe a lot? But the real answer is so much stranger and cooler than you can imagine. Let's keep that question in the back of our minds as we get started.
To really get what's happening in those gaps, we've got to start at the beginning. We need to look at our basic number toolkit, the numbers we came up with to solve the first and most obvious problems in the world.
So we start with the simplest, right? The natural numbers. 1, 2, 3, and so on. Perfect for counting your sheep. But what happens when you have no sheep? Well, for that, we had to invent the number 0, which gives us the whole numbers. And then, life gets complicated. You've got debts, you've got freezing temperatures. So we invented negative numbers. And boom, we get the integers. Each new set solved a brand new problem. But if you plot these on a line, you can see there is just a ton of empty space.
So what on earth is living in those huge, empty spaces between the integers? Well, to fill those gaps, we needed to invent a much more powerful type of number.
Now, the official math book definition sounds a little intimidating, I'll admit. A rational number is any number that can be written as a ratio, m over n, where m and n are both integers. There's just one crucial rule. N, the number on the bottom, cannot be 0. Yeah, dividing by 0 is a big no-no. It breaks math.
But what does that all really boil down to? It's actually super simple. It's a fraction. That's it. Any number you can write as a fraction, 1/2, 3/4, even something weird like 7/3, they're all rational numbers. And just like that, we have this incredible new tool to start naming all those points between the whole numbers.
Okay, so this is great. We've got fractions, but that opens up a whole new can of worms. How do we know exactly where a fraction is supposed to go on the number line, and how do you tell which of two different fractions is actually the bigger one?
Let's just try one. Say 7/3. The method is actually pretty elegant. The denominator, the bottom number, 3, tells you what size your slices are. So you chop up each whole unit on your number line into 3 equal little parts. Then the numerator, the top number, 7, tells you how many of those little slices to count. You just start at 0 and count out 7 of them. 1, 2, 3, and there you go. That's exactly where 7/3 lives. All right, on to the next challenge. Which one of these is bigger, 5/4 or 2/3? See, their denominators are different, so it's like we're comparing apples and oranges, or quarters of a pizza and thirds of a pizza. It's not immediately obvious which one gives you more pizza. Now, the classic method, the one we all learned in school, is to find a common denominator. Basically, we're going to recut both pizzas so they have the same number of slices. In this case, we can turn them both into 12ths. So 5/4 becomes 15/12, and 2/3 becomes 8/12. Now it's easy, right? 15 slices is obviously more than 8 slices, so 5/4 is the winner.
But let me give you a little pro tip here, a fantastic shortcut. It's called cross multiplication. All you do is multiply diagonally. So for 5/4 and 2/3, you multiply 5 times 3, which is 15. Then you multiply 4 times 2, which is 8. Since 15 is bigger than 8, the first fraction, 5/4, has to be bigger. It is so much faster.
So we've seen rational numbers as fractions, but they have this other secret identity that we use all the time, decimals. It turns out every single one of these fractions can be written as a decimal, and they have a very distinct, very predictable personality.
Rational decimals really only come in 2 flavors. First, you've got the ones that terminate. They just end. Think of 7 divided by 4. You get 1.75. That's it. Story's over. The other type is non-terminating, but, and this is the key, recurring. It repeats. Check out 7 divided by 6. You get 1.166666, and that 6 just goes on forever in a nice, neat pattern. So here's the rule. If a decimal ends, or if it falls into a repeating loop, you can be sure it's a rational number.
Okay, let's take a breath. We started with integers. Then we filled in the gaps with a literal infinity of fractions. I mean, the number line has to be completely jam-packed now, right? It feels impossible for there to be any space left. But there is. And what's living in those tiny hidden gaps is a totally different beast.
And the clue that blew this whole mystery open didn't come from just playing with numbers. It came from geometry, from a really simple question that totally broke the brains of the ancient Greeks. Just picture a perfect square, one unit on each side. The question is,
What is the exact length of the diagonal?
To figure this out, we need that famous theorem. You remember it, the Pythagorean theorem. We take one side squared, which is 1 times 1, so 1, plus the other side squared, also 1. And that equals the diagonal's length squared. So 1 plus 1 is 2. The diagonal squared is 2.
That means the exact length has to be the square root of 2. Okay, but what kind of number is that? The Greeks, who were obsessed with the idea that the whole universe was built on nice simple fractions, they tried everything to write this number down as a fraction. And they couldn't. It was impossible. They had stumbled upon something completely new, and frankly, it freaked them out.
So what they found is what we now call an irrational number. And here's what makes it so different. If you write it as a decimal, it goes on forever. But unlike our friendly repeating decimals, this one never settles into a pattern. It's infinite chaos, infinitely long and infinitely unpredictable.
And the square root of 2 isn't some lonely weirdo. It's got a whole family of other irrational roots, like the square root of 3, the square root of 5, and on and on. And you know who else is in this exclusive club? One of the most famous numbers of all time, pi. Yep, that number you need for anything involving a circle, it's irrational. Its decimal digits go on forever with no pattern in sight.
So here we are. We've got our two teams. We've got the orderly, predictable, rational numbers, and we've got the wild, unpredictable, irrational numbers. It is finally time to bring them all together.
When you take every single rational number and you pour in every single irrational number and you mix them all up into one giant collection, you get what mathematicians call the real numbers. This is it. This is every possible point on the number line all accounted for.
And with that, we've done it. The number line isn't a bunch of dots with spaces anymore. It is now a perfectly solid, continuous, unbroken line. Every single possible length, every distance you can imagine, has a home somewhere on this line. There are no more gaps. It's finally complete.
So we've filled every single point on this one-dimensional line. It holds every number needed to measure anything in our physical world. But that leads to one last, mind-bending question. What if a number didn't have to live on a line? What if a number could exist in 2 dimensions, with a real part and, well, something else entirely? What could that possibly look like? Something to think about.